button? Okay, welcome back everybody for the first afternoon session. The next speaker is Hansen from Cambridge. Will tell about infinite dimensional continuous compressed sensing in physics.
Well, thanks so much, and I just want to say thanks so much for the invitation. I'm really excited to be here. This is my first physics conference. I'm really a mathematician, but I do work with physicists and engineers on a daily basis, so hopefully I'll be able to make this interesting for you. But I'm not here just to give a talk. I'm here to learn, so I hope that I get the chance to talk to people afterwards. So I'm going to be talking about compressed sensing in physics, and in particular, continuous compressed sensing. So to give you a little bit of motivation, I'm going to start with a list of problems, a list of compressed sensing problems. The first one on the list is MRI. This is probably the flagship of applications of compressed sensing these days. You have other areas of medical imaging, X-ray computed tomography, CT, and then the whole sort of tomography family. There's nuclear magnetic resonance, which is close to MRI physically, but actually the fields are very different. Electron microscopy, tomography, reflection seismology, radio interferometry, helium atom scattering, and last but not least, fluorescence microscopy. So if you look at this list, what they have in common is that they are indeed problems that are formulated over the continuum, simply because they're physical problems. And most of them, with the exception of fluorescence microscopy, can be described by either the Fourier transform or the Rodin transform. And what they also are, they are inverse problems in the following way. I have some unknown function here that I don't know, and what I see because of the sampling apparatus is a transform of it. And the task is to reconstruct from that transform. Now, if you have a tomography problem with the Rodin transform and you have what's called a parallel beam, you can do the Fourier slice theorem and also convert this to a Fourier problem. So I'm going to be talking a lot about Fourier problems today, not just because it's important, but that's one of the main issues with compressed sensing. It doesn't mean that you only need Fourier measurements to get compressed sensing to work. Now, if you pick up a book on compressed sensing, it will actually start with a completely different setup. It will start with a discrete setup. And it may look like a little bit of a contradiction, given that list that I showed you, even with the flagships of compressed sensing in applications being completely continuous, if you will, or infinite dimensional. So what I'm going to do now is that I'm going to give you sort of a 101 introduction to compressed sensing that's going to last for about 2 minutes to essentially give you the setup and also what I call the pillars of compressed sensing. So if you pick up a book on compressed sensing, it's going to start with this. It's a finite dimensional inverse problem. And of course, solving that, inverting that matrix is really not rocket science if you know that it's invertible, right? And that's not what compressed sensing is all about. What it's all about is the following problem. What if I don't have enough resources to take all the samples in that, say, measurement vector y? But suppose I have the luxury of choosing the samples of my choosing. So suppose I could take the first, second, fifth, 29th component of that vector. Well, I hit this now with a projection that picks out these elements. But what I'm ended up with now is a linear system, but it's underdetermined. So there's way too many solutions, one of them being the guy that I'm interested in, but a lot of them that I really don't care about. And then sort of miraculously, by solving this convex optimization problem, this L1 problem here, one can actually recover that x0 under certain assumptions. And actually what one can show is that if U here is an isometry, and if your sampling is uniformly at random, then the number of samples that you need to be able to reconstruct this guy of interest is given by this. There's a constant C that we, to be honest, don't know what is. My rough guess is that it's about 2, but we don't really know what it is. And it's the dimension. This mu here is what we call the coherence parameter. It's simply the maximum elements of the matrix squared. And then the key part here is this S. This is what we refer to as the sparsity. The number of non-zero coefficients of that x0. It would be a little too much if I could say that I could recover an arbitrary vector x0, right? So it has to have some structure, and that's the sparsity. It has to have few non-zero coefficients. Then there's a couple of log factors. There's a log here with an epsilon. And this is because there's a chance that I may not be able to recover it, but that chance is small, and for that to shrink, I essentially need to pay a log factor there. And then I also have to pay a log factor in the dimension. But what it says is that up to these reasonably harmless log factors, it is linear, at least if I have this parameter here to be 1 over n, so that kills that. The number of samples roughly is linear in the sparsity up to a log factor, which is nice, right? Now, the reason why I show you this equation here is that I would like to show you what I call the pillars of compressed sensing. The first one is the sparsity. You need to have some kind of assumption on the vector, few non-zero components, right? The incoherence, you need the matrix to be sort of flat, to be spread out. You don't want it to be like the identity, right? You want it to be spread out, right? And the sampling that you're going to do is uniform random subsampling. This is what you will essentially get if you start with a book on compressed sensing or a survey paper. So what I'm going to do now is that I'm going to talk a little bit about the different point of view, namely to essentially phrase this as an infinite dimensional problem. And I'm going to give you a little bit of motivation and show you the results. But more importantly, I'm going to show you how that also affects the theory of compressed sensing and how we can understand that in related to actual physical problems. So I'm going to start with a very basic MRI problem. And I'm going to do this in 1D. So I have my unknown function g, and I can see the Fourier transform of it. And I assume that the support of my g is compact. And that means that I can sample the f, the Fourier transform of it, at what we call the Nyquist rate. And with that, we can actually recover, at least in the L2 sense, the g from these samples. This is simply the Fourier series, right? Now, of course, I don't have access to all these infinitely many samples, so I have to truncate. Now I have finitely many samples, and I get the truncated Fourier series, which, of course, is going to approximate the guy that I want. And if I do this now on a very simple test, you may ask, are people really interested in actually recovering the Haar wavelet? No, they're not. This is a toy example to illustrate the issue, right? But I'm going to take my g here to be the Haar wavelet. And I'm doing that also for the purpose of showing you the idea of sparsity. If I express this function here in, say, a wavelet expansion, it's super duper sparse. There's only one component in that vector, right? That is non-zero. I'm going to test this. This is a super duper sparse compressed sensing problem. Now, if I try to approximate that with this gn function, the truncated Fourier series, this is what I get. Nothing more, nothing less. This is what we know, how bad or good the truncated Fourier series approximates functions. That's something we know very well. Now, the important thing, though, is that I can use this truncated Fourier series to write this compressed sensing problem here in the format of a y and then a finite matrix and an x. And this is done very, very simply. If I rasterize this gn here on an equidistant grid, you immediately see that, I'm just summing up these exponentials, meaning that I can write this now as y being the vector of all these samples, and then this x here is simply a rasterized version of that gn, and u here is the discrete Fourier transform. So we have discretized the infinite dimensional MRI problem to now a finite dimensional problem. But the key thing, however, is that this guy here now, it is not the true solution anymore, right? This is an approximation to the true solution. Now, I'm going to try now and see if I can apply compressed sensing to this problem. And since I have the Haar wavelet, I assume that if I hit this x here now with a discrete wavelet transform corresponding to the Haar wavelet, that should be a very sparse thing, right? And if that's the case, I should be able to randomly sample, solve my L1 optimization problem, and here now I've hit this on the right-hand side with discrete Haar wavelet to make it sparse, and then hope that I can recover. So let's see what's going on. Oops. I'm getting this guy, which is not the perfect thing, right? I serve you a super sparse problem, and I don't think I can claim that that's very impressive. So the question is, why does this happen? And the key thing is that I have discretized this in a, what should I say, non-effective way. Oops. Did I do something wrong?
No, it happened already once.
Yeah, true.
Yeah, it's your fault.
Again. No.
Try to, in the meanwhile, yeah. Why don't you hang it down? Yeah.
I can also scream.
No, it's that object there that I will give. You know the story already.
So we take 5 minutes, yes.
Yeah, because I think when it try to look.
Hello.
Yes.
Good.
Fine.
There is a step,
So it's the only thing that
We started at 35.
started at 45 because there are I don't know if it's very right. Why does this happen?
That's a good question also for this.
Come on.
You know, it has to turn green.
Well, if anybody has a good stand-up routine, now is the time.
While we're waiting,
Yes, please. Oh, and you can ask questions.
the initial requirement on your matrix was that it should be sparse,
Yeah, no, not the matrix, the vector.
but that you had a sparsity factor.
Yeah, but that was only on the vector. The matrix should be spread out. It should be flat. But the sparsity is only on the vector that I'm trying to recover. So the vector should have few non-zero coefficients. So I won't be able to recover any vector, but if I have a vector that has only a few non-zero coefficients, then that essentially allows me to do the subsampling. That's the, if I don't have that, I can't do very much. But it's the idea that with this extra assumption of sparsity, then you can do things.
Physically, what does that mean?
Physically, what it means, that it's sparse. What it means is that there's a way of representing your signal that essentially you don't need that much information. So if you take an image, take your iPhone, and you store that now as a compressed version, what it does is that it computes the wavelet coefficients of it, throws away 99% of it, keeps only 1%, sets everything else to 0, and that's what you're storing on your phone.
So for a Fourier transform, it would mean the signal has just a few Fourier components.
For example. But so if you do JPEG, it's Fourier. If you do JPEG 2000, it's wavelets. So essentially, you can describe. So physically, it means that you can describe this in a clever way, with not too much information. And images typically are very sparse in wavelets, for example. Oh, now we're back again. Okay, good. Sorry. Yeah. Okay. So why did this happen? Well, you see, this is the approximation that I have. So if I actually did full sampling, okay, yes.
Naive question. So on the right, the
Yes.
plot actually looks pretty good to me. What is your measure of something being good or bad?
I wanted to recover this perfectly. I wanted to nail it completely. I want to get that guy. I'm demanding, very demanding. I want that.
So like
I
a
don't want
1%
this.
error or?
Zero error. Zero error. That's what I want. This is super duper sparse. I'm claiming that I can recover things, according to this here, and S here in this case should be 1. I should be able to really, really kick ass, right? So I'm not happy with this.
Okay.
Now you see, the thing here is that this is what I would get if I do full sampling, right? Then it's just inversion. So how on earth can I then think that I could get anything better here. And in fact, this transformation now does not give me the wavelet coefficients of the original signal. It gives me the wavelet coefficients of the truncated Fourier series, of the wiggly guy. That's not sparse in wavelet, right? So that's why I'm getting garbage. And then the whole issue is that, well, physical problems are actually continuous and infinite dimensional, so why should I not try to solve the actual problem from the get-go? So that's what I'm going to try to do now, right? So now I'm going to be a little more abstract. So I assume now that my x0, my unknown, lives in some Hilbert space, some separable Hilbert space. I have some orthobasis so that I can describe this now simply with a vector of coefficients. But I don't see that. The only thing that I can see through my MRI machine is essentially some linear functional acting on that thing, Fourier coefficients, right? So that's the only thing that I can see, and I would like to recover essentially these coefficients from those measurements. And if I set that up, this becomes very easily an infinite system of equations, right? So why can't I just pretend that I have an infinite computer and I'm going to do exactly what you do in finite dimensions with compressed sensing, just in infinite dimensions, right? Well, modulo the fact that I don't have an infinite computer, but let's leave that aside, okay? So if I had an infinite computer, I could work with this, but I wouldn't be interested in taking infinitely many samples even if I had an infinite computer, because the MRI machine can't give me infinitely many samples. It can give me only finitely many. But I could do the following as a thought experiment. Why don't I simply try to do some subsampling of this infinite problem, and then solve L1, because apparently that's going to be good, and pretend that I had an infinite computer that could solve this infinite optimization problem. It has finite by infinite, if you will. And I could actually write theorems about that, and if I do, I will realize that that actually works pretty well. It's just one hurdle: I don't have that infinite computer. So to compensate for that, I'm going to pretend that I almost have that and say, I'm going to hit that on a projection on the right that projects from 1 to R. And then if you can show that as R blows up, solutions to this problem here will converge to solutions to that problem, now we're getting somewhere. And in certain cases, then you can have bounds on how large you need to pick that R, for example. And what I'm doing now is that I'm solving directly for the coefficients. So for the original problem, if I wanted to get the actual wavelet coefficients, these are going to be the unknowns here. So I'm going to show you a very simple example. I'm not going to take the simple HAR. It would actually take me, I think, 6 samples to perfectly reconstruct that. So that's a toy problem. Now I'm going to do something more interesting. So this is at least, it's a piecewise smooth, so you can argue that this could sort of look like a slice of an image. This is a piecewise smooth function. This is a completely smooth function. I'm going to simply try the 2 different approaches. And I'm taking exactly the same samples. This is important. I don't do a different sampling strategy. Exactly the same amount of information. It is just the reconstruction based on the finite dimensional discretization, or say the infinite dimensional discretization. And this is what you get. This is what you get from the finite, and you have essentially all the wiggles here because you have tried to go via the truncated Fourier series. Whereas this one here goes directly for the wavelet coefficients and then clears it up. In the case of the smooth function, I didn't even bother showing the reconstruction because they're pretty good. This is the error of a discrete thing. This is the error for the sort of continuous infinite dimensional one. And you gain a couple of orders of magnitude. Here's a slightly more realistic example from electron tomography. Here's the original. Here's the zoomed original.
Sorry.
Yeah, please.
Again, very naive question. So the previous slide, the purple one on the right,
This is
you
the-
obtained by increasing the size of your projection, and then at some point you stop because you
Yeah,
see.
I sort of swept that under the rug how I chose my R. In this case, it's actually twice the range I did.
So it's not like a huge factor.
No. That's a very good point, yes.
Okay.
And also I can do the computations fast. There's a lot of things that I sweep under the rug here. But the point is that both of these things take the same amount of samples. This here is just post-processing work, if you see what I mean.
Right.
So the competition is you give the samples, and then you fight to get the best reconstruction. You know. And actually, time-wise, this would actually take roughly the same time computation as well. But that's actually a very good point. All right, and then you see here, this is, you see the ripples. It's the same thing as we had before. This one goes directly for the coefficients, and it clears things up. So that's essentially the first part to give you a little bit of motivation for what we're doing this sort of infinite dimensional compressed sensing. And it does give you an improvement. The improvements will vary depending on your functions. But more importantly, what it also gives you is it gives you an insight to understand how compressed sensing works for physical problems. And that's what I'm going to cover now. Because the interesting thing is that these three pillars, sparsity, incoherence, and uniform random sampling, are actually not there on that list of problems that I showed you. Not even in the MRI example, which is one of the flagships. And that may seem a little contradictory. So that's what I'm going to go through now. So if you actually start with uniform random subsampling in MRI, and I now deliberately give you a finite dimensional discretization here, the same phenomenon will happen if I do the infinite. If you actually take 5% random subsampling, so this is the frequency, it plays a little hard to see here on this projector, but there's really just small dots spread everywhere. And if I try to reconstruct here, you may think that I'm trying to reconstruct a picture of a dark room. I'm not doing that. I'm desperately trying to actually reconstruct that brain image. Not very successfully. And then instead, the alternative sampling pattern is to take the same amount of samples, 2.5% here, they're fixed, and then 2.5%, it's hard to see here, it's just a cloud sort of points here, which are uniformly distributed. And then suddenly I can actually get something. It's not that good. And actually, if I do sort of a shotgun thing, where I sort of place them in a sort of cloud like that, suddenly I can clear up the image. So the first thing we learn is that uniform random subsampling, certainly in MRI, is not going to work. The second thing is that you realize that, oh, actually there's tons of different sampling patterns, and they will give you different quality. So how do you set the sampling pattern? Right. But that's the first sort of tick the box. Uniform random subsampling will, I should say not will never work, but will rarely work in physics. So what about the idea of sparsity? So the idea of sparsity is that your vector has little information in the way that there's a few number of non-zeros. But the location of them are arbitrary. And that sounds reasonable, right? Because why would you have a theory where you need to know where they are? They should be somewhere, but you don't need to know where they are, right? So if it's really the case that the success of your recovery is completely independent of the location of the coefficients, I should be able to perform what I call the flip test. The flip test is simply just flipping the coefficients and see what happens. So I take this brain image that I have. I use the discrete model of MRI just for fun. I use the discrete wavelet transform to make it sparse. I do some subsampling, not uniformly at random, because we saw that gives me garbage. And then I recover with my L1 optimization, and I'm getting, these are two different types of reconstructions based on two different types of probability distributions that give me sort of this cloud where it's centered around the zero frequency. But I don't really care about what they are. The only thing that I care about is that they look reasonably nice. Now, what I'm asking is the success of that recovery independent of the location of the coefficients? So if they are, I should be able to take that. These are the wavelet coefficients. I can compute them because I know this. I have the true solution. I just flip it, right? And then I plug that in. Of course, I get a new measurement vector. I solve that. And if it really was the case that the success was independent of the location, I should be able to solve that and flip it back and get the same thing, or at least close to it. Did that make sense? Hopefully. What do you think happens? I sort of hyped this up, right? So you get complete garbage. So the point is that actually the location does matter. And then you can ask yourself, is this sparsity model really the right model? Because clearly, I don't want the doctor to operate on my brain if this is what he sees. right? So regarding the uniform subsampling, that may not be there. Sparsity is an issue. I'm going to address this later on. But the third one is the incoherence. We wanted the matrix to be sort of spread out, right? That was the key thing in the estimate. But if I actually look at this matrix here, the combination of the discrete Fourier transform and the discrete wavelet transform, it is 1. It's the worst thing. I want this to be 1 over n, right? So I'm getting the worst kind of thing, and I'm selling this as one of the pillars. And not only does this not happen for any n, it doesn't happen for any Debussy wavelets, it actually doesn't happen for any wavelet. So now you may ask, what on earth is really going on? Now, the reason why is because there is an infinite dimensionality essentially lurking in the background here. There is essentially a physical problem that requires this infinite dimensionality. Because if I look now at the weak operator topology limit of this matrix, so the WOT, that's just fancy wordings for pointwise convergence of the matrix elements. So this actually converges to a matrix, an infinite matrix that looks like this. It has some phi's here. These are actually the wavelets, and these psi's here are going to be the complex exponentials coming from the Fourier measurements, right? And this is an infinite matrix. And of course, this infinite matrix does have a fixed coherence. That doesn't change with the dimension. It is an infinite dimensional thing. Hence, there's no way that I can essentially beat this barrier. There's no chance that I can essentially have 1 over n here, because it converges to this guy. So there's no way that you can have it. And the key thing here is the underlying infinite dimensionality. So then you may ask, but why does this work at all? And the reason why it works is that it is really not incoherent, but it's asymptotically incoherent. So what I've showed you here is a section of this infinite matrix. I have reshuffled a little bit. So the measurement that corresponds to 0 frequency is here. And then this here goes to minus infinity in Fourier, if you will, and this goes to plus infinity in Fourier. And white here is 1, and black is 0. So you want 0, you want black. So it's terrible here, but out here it's really nice. If I change to a Legendre polynomial expansion instead of a wavelet, then it looks like this, completely different. But it's still asymptotic. It's getting better and better out here than compared to that one. So what about the sparsity? Well, the sparsity is also asymptotic. So here I've simply computed the wavelet coefficients of an image. And what you will see here is that up here, the first part of the expansion, it is not very sparse. You have dense coefficients in this area here, but as you move out in the expansion, it becomes very, very nice and sparse. And the beauty is that this asymptotic sparsity and this asymptotic incoherence actually align beautifully. And that's how you design your sampling pattern to fit this. But how to set the sampling pattern is a science on its own. So this is essentially what's going on. And an effect of this is probably the most important effect to understand if you want to boost compressed sensing and get it to work. And that is the resolution dependence. So before I'm going to discuss this, I'm just going to show you a very simple, this is a real-life MRI example. The first part here, I see 256 squared Fourier coefficients. That's the output that I'm getting from my machine. This is what I'm getting. This is the full sampling that I'm getting. And here I have subsampled from that according to that subsampling strategy, 5%. You probably don't want a doctor to operate on your brain if this is the output. But check what happens when I enhance the resolution. So now I go to 512. It's still not great compared to full sampling. If I blow it up to 24, now we're getting somewhere. And at 2048, I have deliberately now not shown you which one is the original and which one is the reconstruction. So this is 20 times speed up. And the reason why this happens is because of this asymptotic phenomenon. because there's an underlying infinite dimensionality here. So when I blow up the resolution, things become more and more sparse, and it also becomes more and more incoherent. And that's how you can get this effect. But the problem with this is that if you wanted to use compressed sensing as a technique to save time, well, it is not going to work very well here. It is only going to work well in this regime here, meaning that you need to take a high resolution and then subsample from that. So what have you gained? Well, you may not have gained any speed, but what you may have gained is essentially increasing resolution on this. So if the lesson is that you need to essentially squeeze the resolution to its highest to get the effect of compressed sensing, maybe you want to use it for resolution enhancing instead. So I'm going to show you a very simple example. This is a synthetic example. When I do these things here, the MRI machine spits out the Fourier coefficients anyway, so I don't need to essentially model this. Here I have to actually compute the true Fourier coefficients of this analytic phantom, which we do. So this is a synthetic experiment, and what we've done is that we've hidden a little brain tumor inside here, and the task is to reconstruct that. So the brain tumor is not that. Here's the brain tumor. And the poor patient of ours suffers from a really, really aggressive cancer, and it's not just aggressive, it's extremely sophisticated. So it's so sophisticated that the brain tumor here actually forms a sentence. And the only cure for the patient is for you to read the sentence. Can you read it? No. So this is what you will get with a full 512 by 512 scan. Now what I'm going to do is that instead of using this 512 full sampling, I'm going to take the same amount of samples, not the same samples though, and I'm going to spread them and I'm going to subsample from a much higher resolution. Because I hope that's going to give me something, because, well, the effect of compressed sensing is better at higher resolution. So here I pay essentially 262,144 pounds, if you will, if I had to pay a pound for each sample. And in this case here, I also pay exactly the same amount. But now you can save a patient. So the lesson here is that you may want to use compressed sensing as a resolution enhancer simply because the asymptotics are going to work for you. In the beginning, when compressed sensing was used in MRI, it was intended as a time saver. And when we cooked these things up, we put this on the archive, but we thought maybe we should alert some of the manufacturers about this because it could be useful for them. So we contacted Siemens, which is one of the largest manufacturers of MRI machines. So they were happy, said essentially, thanks so much for getting in touch. However, we have already implemented your stuff on our machines. So, and they already had written a report on it. So they concluded with this technique that they can indeed improve the resolution, but more importantly, they state that it implies that the full potential of compressed sensing is unleashed only if asymptotic sparsity and asymptotic incoherence is achieved, and also suggests that compressed sensing might be better used to increase the spatial resolution rather than accelerating the data acquisition because of this phenomenon. So we were, of course, happy that Siemens tried this and essentially verified the theoretical and synthetic experiment that we had. But we wanted to test this ourselves because we had a feeling that Siemens hadn't set the subsampling pattern to its optimum. So we started a project with a radiologist in Cambridge. So this is our experiment. It's done with Bogdan Roman, who is essentially running the MRI experiments in his member of my group. It's his brain. So we're getting really the stuff from the machine. There's no cheating here. Martin did all the sampling. He's the head MRI guy at Addenbrooke's hospital. What we're doing here is that we're taking a full scan of a brain, and we're zooming in on this part here. So this is what you will see. This takes 15 minutes of scan time. Now, what we're doing here instead is to take the same amount of scanning time, but we're sampling from a much higher region of frequencies and run our compressed sensing stuff. And now we're not comparing sampling. it is a true comparison, it's time. Because radiologists don't care if you say, okay, I sample 30%. They'll say, I don't care. You need to show me the time because the acquisition, if you have to move around, actually take samples of the machine, that's the only thing that counts. So that one takes 15 minutes and this one takes 15 minutes. And it's likely that you want the doctor to operate on your brain. If he saw that image, then that image. Right? So it is indeed the case that you can essentially do resolution enhancing at MRI quite substantially. If you go to Cambridge University Hospital and get an MRI scan today, you will get this, but in a year's time, it could very well be the case that you get this one here, which might be better. Anyway, so what I try to convey with this is that there is this underlying continuity or infinite dimensionality of problems in physics. And that means that we need to essentially rephrase these pillars a little bit. You can essentially just take them and add asymptotic in front of them. And then the random subsampling, the uniform random subsampling, has to be replaced by what we call a multi-level subsampling scheme, where essentially you take the structure of the problem into account. So what I'm going to do now is that I'm going to rush through a little bit of the theory. The purpose here is just to show you that, well, we sort of hopefully know a little bit of what we're doing. But I'm not going to go into the details a lot. But I'm just going to give you this, the definitions and also a theorem at the very end with the estimates. So instead of just defining sparsity, we define the sparsity in levels. So instead of having one number that governs the sparsity, there should be a vector, S here, with S1 and SR, depending on the levels, which is exactly what is going on in wavelengths. There's a sparsity here, 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 and they're different depending on where you are in the expansion of your function. And what happens then is that when you actually look at the estimates, I just wanted to define this because it will show up in the theoretical estimate, is that when you're trying to essentially recover your F, the estimate that you're going to get is that you're going to get essentially the best approximation to your beta with something in this class which is sparse in levels. And the way you sample is that you also imitate this kind of level structure. So instead of having one uniform random way of sampling, you simply take different kinds of omegas, in this case R, with different densities, and simply glue them together. It will look a little bit like this. You can see the level structure here. And this you can tailor completely depending on the structure of your signal and the structure of the sampling operator that you have, and this incoherence. And this is also an important part. We need the local incoherence instead of this global incoherence, which is essentially just a sledgehammer, whereas this one here is the scalpel. And it's exactly as we see this on the figure, because if I look at the incoherence here, it is completely different from where it is here. So you really need this scalpel to understand how to set your sampling. And then finally, we solve this problem here, and then the estimates are like this. This tells us how much I need to sample in each level. And the key part is that it depends on these local sparsities and these local incoherences. And from this, you can essentially read out exactly what is going on in this flip test. Because if I flip these coefficients, I will have to sample completely differently. Not only just differently, but even more, because now this asymptotic sparsity and asymptotic incoherence may not align anymore. So this is a much, much more difficult thing to recover if I suddenly flip the coefficients. And then what you end up with here in the estimate is that you see this best S-term approximation, and then this is the noise part if you're solving the noisy optimization problem. Okay, so that was essentially the final sum up of the theoretical parts. There's quite a lot of things going on under the hood here. But essentially the take-home message is that if you understand the modality of your problem, the transform, if you understand how this local incoherence behaves, and also the sparsity structure of your signal, then you can tailor your sampling and you will do well when you do compressed sensing. If you don't know that, it is likely that you're going to get very suboptimal results. I'm just going to end because I have talked a lot about MRI. I just want to show you another effect of this continuous compressed sensing approach. So this is in helium atom scattering. There's a group at Cavendish Laboratory that does this. And their problem is very different from MRI. They also have Fourier measurements. So this is what their machine gives them. And this is the unknown function that they're interested in. So whereas the MRI problem sort of stops here, they want more. So what they do is that they do a nonlinear transformation of variables to get here, and then take a Fourier transform of that, and they're interested in both these guys as well. But that's not an easy thing to do if you're working over the discrete. So if you're doing this with this sort of infinite dimensional discretization, you get these things completely for free, and you don't need to do anything else. So this was sort of a byproduct. It was not essentially intentional that we designed these for these things. They just realized, actually, this is pretty convenient. So this is a paper that we just published, and it's just to show that it's not just MRI, you can do these things. And more and more physical problems of interest, it seems that we can apply compressed sensing. But with that, I will thank you so much for your attention.
Thank you, Anders. Questions from the audience? Philippe?
So maybe I understood wrong. My impression is that in your problem, the input is sparse,
Yes.
but exact.
Yes.
In our problem, typically, the input is not sparse and noisy.
But when you say non-sparse, what do you mean by that?
We measure all the coefficients in some basis.
You mean the acquisition device takes all the samples?
Right.
So
We do it by Monte Carlo, so Monte Carlo is ergodic, it goes everywhere.
right. So the purpose of compressed sensing is to say that, well, if you have some extra structure, then you may not need to take all those samples.
Well, we get all these. If we sample everything because our algorithm is ergodic. On the other hand, the results are noisy. They have statistical noise.
I see. Right.
Okay, can you help us reduce the noise?
Well, okay. It's actually a fascinating question. Let me see if I can address it. In this example here, actually it's not that great, but it's actually a very good point. If I took full sampling in an MRI example, and I looked at the reconstruction there, what will happen? The noise is white in MRI, so that means that the high frequency are getting much more noise compared to the low frequency, because that's where we have a lot of amplitude. And since I've taken all the samples, the sum of the noise is essentially summing up everything that I've sampled there. If you do a subsampling of that, I'm actually getting less noise. So if you're doing a compressed sensing on this, you actually may see less noise in the reconstruction. However, for that to work, I still need some kind of sparsity. So if your original signal is not sparse at all, but here one has to add in a little asterisk. Sparsity depends on the representation of the signal. So for example, if I take a polynomial is not sparse in a Harvey-Wildert decomposition. But a polynomial is, of course, very sparse if I use a polynomial representation. An analytic function may not be sparse in a Harvey-Wildert, but very sparse in a Hermite polynomial expansion. So it depends on what you can actually choose for it. So it could be that the problem is sparse, but you need to find the right expansion to get it to be sparse, if that made any sense.
Yeah, a question, Kurt, your question?
I had a question for help. So I had a similar question. So
Yes.
we often don't use Fourier transforms with Laplace transform.
Okay.
So is it applicable for Laplace?
Could very well be the case. I haven't used it. So the lesson is essentially that if you have a transform like the Fourier, which is a unitary transformation, that is a nice thing. That doesn't mean that if you use for something that like the Rado transform, which is much worse, it's a compact operator, that you cannot do it. So I would say I will have to see. It's likely that you will get not as good, but it doesn't mean that you can't use it at all. So it's sort of completely up for grabs.
Is there time for another question? Last one, Antonio?
While doing this sampling, what we are interested is not only the measure,
Yes.
but also the error. Are you able to, by subsampling, tell us how far is your output number from an actual precise definition of the...
That's a very good point. That's a very good point. Okay. Ironically, I showed you actually here a theoretical result, which is actually in the finite dimensional case. I could have shown you an infinite dimensional problem here as well. In that case, to get the error here, I will have to say something about the range of the samples. So if I wanted to do an MRI thing, I will have to say, well, I need to see frequencies up to this. And then I'm going to subsample from frequencies up to that. And then I will get an error like this. But I need to have an understanding of how much frequencies I need to see to get essentially the wavelet coefficient from that information. That's not trivial. That depends on the expansion of the signal itself. In other words, if I, for example, have an expansion in wavelets, or if I have an expansion in Legendre polynomials, the amount of Fourier frequencies that I need to see to get the first 59 Legendre polynomials, or to see the first 59 wavelet coefficients, are very, very different. So that's a very subtle point, and not trivial at all, because the information lies now in the coefficients in the expansion. So that means that to be able to answer that, we need to know essentially how do we expand, because everything here is in terms of the vectors. So when you're getting the coefficients in the vector, that's the error, and then you translate that into the actual function. So that it's a very good point, but very, very subtle, and not at all easy. But there are results, but this is probably one of the toughest ones.
Okay, so let's thank Anders again. And the next speaker is Hiromichi Nishimura will tell us about complex spectrum of QCD at finite density.